Hello everyone, today in this video we'll be learning about fifth module of 18 CS42 and it has to do with the backtracking. Okay, so there are many concepts in which backtracking is used, so let's learn one by one. And if you like this video, hit the like button and don't forget to subscribe to my channel. So let's understand first what is backtracking. Suppose that there are three persons A, B and C and these are three seats. Okay, means A can sit here or B or C. So many possibilities are there. So how many possibilities are there for three persons? It's three factorial possibilities, right? So in backtracking we'll be finding out all the possible solutions. Okay, so let's consider an example here. For representing that we'll be using state space tree. Okay, so to represent the possibilities of the three persons sitting here, what we can do is first we can take a node here. This is the state space tree. In the first position, A can sit, right? So I'll be writing here A. In the next position, either B or C can sit. So first I'll be taking B. So I'll be making here B, and then C can sit here. So I'll be making here C. This is one of the possibility. Now there are no more persons, so I'll be erasing the last one, which is C. So now C is not there, and what we have is, if you erase C you will have to come back to B. Now coming back to B, what we have is no more persons are there from B, because only if after B C can only sit, so we'll come back from B to A. Okay, when we come back from B to A, then we have at A either C can sit and B can sit. Since B is already sat, we can place here C. Okay, so C will sit here. Okay, then after C, what's the possibility? B. So then B will be sitting here. So this is second possibility. Then coming back again from B to C and C to A. From A, who can sit? C or B, both are done. Then coming back again to the root node. Coming back to the root node, who can sit at the first position? At the first position, either B or C can sit, right? Means initially we can place here, see here. Initially we can place here B, right? So then B will be placed here first, and then what's the possibility? C or A. So I'll be first placing A here, then what's left? C. So this is one of the another solution. And coming back from here at A, there is no other possibility. We'll come back to B, and from B we'll place the next position as C, then A. This is the second possibility. We'll be coming back two times till the root node. Then first we'll be placing C, and then two possibilities are there, either B or A. From A it will be to B, and from B it will be A. So this is what state space tree is. Means there will be all possibilities. The first possibility, second one, third, fourth, fifth, sixth. All right, so we'll be representing all the possibilities using a state space tree. Note here one thing very carefully. What we are doing is we are placing one node, then moving on to the next level, and then we are placing, then we are moving on to the next level. If you follow this way, this is known as backtracking. Okay, there's another method which is known as branch and bound. Let's see how that works. The final tree generated is the same tree, but the approach is very different. In this in backtracking we used in backtracking we use DFS, because one node we placed, then we went on to the next one, and then we went on to the next one. But in this one, which is branch and bound, we'll be using BFS. Let's see how it is. In BFS, if you remember, what happens is firstly A, B and C can be placed. So we'll be writing here A can be placed, then B, then C, right, in the first place. Then after that, from A, what all can be placed? From A, B can be placed at one possible solution, and C at the other possible solution. From B also we can place A and C, and from C we can place B or A. So in that way we are um, first visiting all the nodes, right? All the possibilities we are visiting, then we are visiting its neighbors, and so on till we reach the end. All right, so in this way if we do, it's known as branch and bound. And remember, branch and bound uses BFS, okay, and backtracking uses DFS. All right, this is the second question, which is n queens problem. So using backtracking, how can you solve n queens problem? Okay, so observe here, we have been so we have to place four queens in this board in these positions, like from first row, or first row, second row, third row and fourth row. first column, second column, third column, and fourth column. Okay, among these cells we have to place 4 queens: q1, q2, q3, and q4. Okay, but there are 3 rules. The first one is they should not be in the same row. For example, I cannot place q1 and q2 in the same row. Okay, and I cannot place q2 and q3 also in the same row. Okay, that will be invalid. That's the first rule. The second rule is they should not be in the same column. That means I cannot place q2 and q4 in the same column. Okay, so I cannot place q1 and q3 also in the same column. That's also invalid. Okay, that's the second rule. The third rule is they should not be in the same diagonal. So if I place q1 here, I cannot place q2 here. Okay, that's invalid. If I place q3 here, I cannot place q4 here. Okay, that's also invalid. Keeping in mind these 3 rules, let's try to see what all the solutions we can generate. Now we have to solve this using backtracking. So firstly we'll be generating the state space tree. Okay, this is the root node. Okay, I'll be keeping in blank because it's a root node here. And in the first position, what I can do is I can pick q1 and place in the first place here, q1. Okay, then what I'll be doing, observe carefully, I have selected q1, right? So I'll be making a arrow here. Okay, and I'll be marking here q1 and which column I placed. In the first column I'll be writing here 1. Okay, then after placing q1, where all I can place q2, I can place q2 in the second row anywhere because I can't place in the same row. So I have to place either here, 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 or here. Okay, 4 possibilities are there, but here I can't place. Why? It's the same row. Okay, so that I will be avoiding. I can place it here. Okay, it's empty column and empty row. I'll be placing q2 in the second column. So I'll be writing here q2 in the second column. Now let's see what happens if I place q2 here. It will be in the same diagonal, right? So I can't move any further from here because it's invalid position. So I'll be writing here x, means I can't move any further. Okay, then I'll be erasing the value of q2 from here. The next possibility is q2 here. Okay, if I place q2 here, where I have placed in the row 3. So q1 in row 1, then q2 in q1 in column 1, then q2 in column 3. Okay, so next possibility is q2 in column 3. Okay, what's the next one? After placing q2, it's a valid position, so we'll move on to q3. q3 can be placed here? No. q3 can be placed here? Yes. So I'll be placing q3 here, q3 at second column. Okay, now let's see if it satisfies. So let's see the third rule, which is diagonal. If I place q3 here, it will be invalidating the third rule, which is it should not be placed in the diagonal. So this is our diagonal forming here, so I can't place q3 here. For that I'll be marking x here and erasing the value of q3 from here. Then can I place q3 here? No. Can I place q3 here? Yes. So if I place q3 here in the fourth row, fourth column, what's the thing? See here, if I place q3 here, it's the row and the column is empty, but diagonal is invalidating. So we have to we can't place q3 there. Okay, so that will be an invalid position. So there is no point in finding out the place for q4 because since anywhere we place, we will not have any place for q3 in this configuration. So you have to change configuration of q2 and see if we can form any possible solution. So next possibility of q2 is from here to here, which is in fourth row, fourth column. Okay, so when we place q2 here in the fourth column, all right, so we'll be placing the third possibility, which is q2 in the fourth column. Then if I place q2 here, then next it's a valid position, I'll move on to q3. q3 can be placed here? No. Here it can be placed? Yes. q3 in the second column. So from here I'll be placing q3 in the second column. Okay, here. Now Q3 is placed, it's a valid position. We'll move on to Q4. Q4 can be placed here? No. It can be placed here? No. It can be placed here? Yes, it can be placed. So I'll be placing Q4 here. So from here I'll be placing Q4 at column 3. Now let's see the third condition, which is diagonal. See, it's invalidating the diagonal condition, so we can't place this one. Okay, so we're marking X here, and we'll move on to the fourth possibility, which is in the fourth column. Can it be placed? No. So here, with this configuration of Q3, we cannot place Q4 at any of these places. So let's move Q3 to this position. When we move Q3 to this position, see here, it's a valid position. It's empty. Row is column is empty and row is empty. So let's write that here. From Q2, Q3 is being placed at row 3, column 3. Okay, but here it invalidates the diagonal condition, so we cannot move any further. So the fourth possibility is here, which I cannot place with the same column as Q2. So I have to change the um, position of Q2, but Q2 cannot be placed any further, so I have to change the position of Q1. So next possibility of Q1 is in the column 2. Here it was placed, now I can place it here. Let's see the configurations now. Q1 in second column. So from here I'll be drawing a graph. Q1 in the second position. Okay, now Q1 is in the second column. Where can I place Q2? Can Q2 be placed here? No, it's a diagonal. Q2 can be placed here? No. Q2 can be placed here? No. Q2 can be placed here? Yes, in the fourth one. So from here, Q2 in the fourth one. I'll be placing Q2 here. Then next Q3. Can I place Q3 here? Yes. In Q1 I can place. There is no diagonal and there is no column and row. So I can place Q3 in the first column. Q3 in the first column. Alright. Then if I place Q3 here, where can I place Q4? See here, Q4 can I place here? No. Here? No. Here? Yes. I can place Q4 in the third column. So we're placing Q4 here in the third column. See here, this is the possible solution and it's a valid combination of the positions. In this configuration, it does not violate the three rules. Okay, so this is one of the possible configurations. When we move on further, what we can find out is there's another configuration which is mirror image of this. See here, if you find out this mirror image, this will come here, this will come here, this will come here, this will come here. Let's make that changes. See, in this position also, there is no row element or diagonal element and column element. Here also the same thing, here also and here also. Okay, so this is second valid position. This how can we represent? Where we have started, Q1 placed, where is Q1 placed? It's at column 3. Then Q2 is placed at column 1. Then Q3 is placed at column 4. Q4 is placed at column 2. Okay, so this is another possible solution which does not violate the three rules. Okay, and these are the only two possible solutions for this problem. And in the exam we have to draw the whole graph, so make a plan in advance how much space it will be required, because in this I didn't plan it, so since it was just meant for the explanation purpose. But in exam you have to draw all the possible solutions like this, and where all it's not possible, mark X there, and where all it's possible, mark a tick there. Okay, and you have to make all the possible solutions in the paper. Okay, this is the next one, which is subset sum problem. So the question will be of this type: apply backtracking to solve below the subset sum problem, and you will have been given with a subset here. And in this subset we have 4 elements: 1, 3, 4 and 6, and we have been given D as 7. Let's look at what is this thing and how to solve subset sum problem using backtracking. Now see, subset sum problem means you have to choose the elements from these subsets such that the sum will be 7. Exactly, it should be 7. Okay, if I choose 1, I can choose 6. 1 and 6 will be a solution, it gives 7. 3 and 4 can be a solution, it gives 7. Rest all the solutions are invalid, okay, because it doesn't give 7. So either I can choose an element or not choose an element. So for that I'll be creating an array here, okay. In this array what I'll have is either I can put here 1 or 0, okay, for 1, 3, 4 and 6. Either I can put here 1 if I select 1, or 0 there if I don't select 1, okay. Same for the other elements also. Now let's see how to solve this using backtracking. See here, initially what we have to do is start from the, see it will be a big graph here, so manage space in advance. So see here, this is the root node which I have taken, and this is the root node which I have taken here. So from here I can first select one or not select one, okay. See here I have two possibilities, right? One, I have mentioned which element I am choosing, okay, and I can either select one or not select one. One means in case if I select one, or in case if I don't select one. There are two possibilities here, okay. And from 1 I can either select 3 or not select 3. So I have two options here. I can select 3 or not select 3. If I don't select 3, I'll be going with this one. If I select 3, I'll be going with this one. Now in addition to that, whenever you select an item or not select an item, you have to write the total sum. Initially total sum is 0, so right here s is equal to 0. Coming here I selected 1, so the sum is 0 plus 1, 1. Then here the sum is 0, okay. And here if I select 3, I'll get the sum as 1 plus 3 is 4, okay. And here I have two options, either I can select 4 or not select 4, okay. So if I select 4, if I don't select 4, okay. Same thing with this also, but first we will solve this one, because it's depth first search, backtracking, so we'll be solving in depth wise, okay. So if I select 4 here or not select 4 here, if I select 4, what will be the cost? 4 plus 4, 8, but that's exceeding 7, so we can't take. See here, the total cost till 3 was 1 plus 3 is 4. If I select 4 here, I can't select because the total cost will then be 4 plus 4, which is 8. I should not get the total cost more than 7. I should get exactly 7, right? So I can't go with this way. The second way is me not selecting 4. If I don't select 4, the sum will be 4 only, because I have not selected this one. So total sum will be 1 plus 3 only, which is 4. Then I have two options, either I can select 6 or not select 6. If I select 6, the sum will be 10. If I don't select 6, the sum will be 4. I need 7, the total sum is 7. So both of these options are invalid. Now the next possibility is not selecting 3, okay, because all these possibilities we have observed, and these three possibilities are not valid. Now let's see, if I don't select 3, what will be the sum? If I don't select 3, the sum will be 1, and then I have two possibilities, either select 4 or not select 4. If I select 4 here, what will be the cost? 1 plus 4, 5. So s will be 5 here, and I can either select 6 or not select 6. If I select 6 here, 5 plus 6, 11, I can't take. If I don't select 6, s will be 5, it's less than 7. And the next one, not selecting 4. If I don't select 4, the sum will be 1 only, and I have two options, selecting 6 or not selecting 6. If I select 6, 1 plus 6, it will be 7. So this is a valid answer. I got the sum here, okay. Mark a tick here. The next one, me not selecting 6, in that case sum will be 1 only, so this case is not possible. So one of the solution I got here, okay. So let's find out the next possibility through not selecting 1. If I don't select 1 here, I'll have the sum as 0, and I have two possibilities of selecting 3 or not selecting 3. If I select 3, the sum will be 3. If I don't select 3, sum will be 0. Then selecting 4 or not selecting 4. If I select 4, then sum will be 7, right? So this is a possible solution. Then if I don't select 4, the sum will be 3. I can't take. From here 0, and I can select 4 or not select 4. If I don't select 4, the sum will be 0. If I select 4, the sum will be 4, okay. And from here I can either select 6 or not select 6. Both of these cases will not give me the answer, because this will give 10 and this will give 4. So both of these cases are not possible. And lastly, from here selecting 6 or not selecting 6. If I select 6, it will be 6, means sum will be 6. If I don't select, the sum will be 0. So both of these options also invalid. Now I have two correct solutions I got here. That was 1 0 0 1. So that is one of the solution. 1 plus 6. The second solution I got is 0 1 1. So after 0 1 1 I got the solution. So the rest of the items I don't need, so I'll mark as 0. So this is the another solution for this problem. Okay. Another topic, Hamiltonian circuit problem. The question you can expect of this type: define Hamiltonian cycle. Hamiltonian cycle means you'll be given with a graph and you have to find out a cycle in a graph. For example, 1 2 7 1. Okay, this is a cycle, but the rule is you cannot repeat one node twice. For example, this is a cycle 1 2 3 6 7 1. Okay, this is a cycle, but you cannot make a cycle in this way: 1 2 3 4 5 6 3 2 1. 3 is getting repeated again. That cannot be a cycle. Node should not repeat and there should be a cycle. Okay, so how many possibilities are there? There are many possibilities. So in Hamiltonian circuit problem, we'll find out all the possible solutions. Okay, so let's see how to do that. Initially I'll be starting from the vertex 1. You can start from any vertex. Okay, so I'll be starting from vertex 1. I'll be writing here 1. Okay, now from 1 where all I can go: 1 to 3, 1 to 2, 1 to 7. So I have three possibilities: 1 to 3, 1 to 2, and 1 to 7. Okay, now I'll be choosing one and going with that one. Okay, 1 to 3. If I go to 3, I have two options: going to 6 or to 4 or to 2. Okay, I have three options here: 2, 6 or 4. So I'll be writing here 2, 6 or 4. Okay, these three options are there. See, first I selected 3, then here I have three options that I wrote here. I'll be selecting one of the options now and moving on further. I'll be selecting 2 here. See, I have written here 2. You can select any of these. Okay, I can reach either to 1 or to 8. I have two options now. Okay, so I'll be writing here 1 or 8. 8 is not possible because it will not give me the solution to a cycle. Cycle means you have to start, you have to end where you started. Okay, that's a condition for the graph being a cycle. So by traveling from 2 to 1, I'll get the solution, so I'll mark it as tick mark. Okay, so that was one solution. The next possibility is from 3 to 6. From 3, if you go to 6, we have two possibilities: 7 and 5. That I'll be marking here 7 and 5. Then I'll be choosing 1, 7. If I go from 7, I have two possibilities: 1 or 8. I'll be writing here 1 or 8. 1 is giving me the solution, 8 is not. Okay, then same thing with 5. When I go to 5, I have one option only: to 4. So I'll be writing here 4, and from 4 I have option to 3. See, if I go to 3 again, it will be repeated. See, the graph was like this, we went, and again I am coming to 3. That's not possible. So I'll be marking a cross here. Okay, so since I cannot repeat 3, I will be marking a cross here. Then next possibility is 1 3 4. So 1, then 3, then 4, then I have possibility to 5, then to 6. From 6 I have two possibilities: 3 or 7. See, 3 I cannot take because I have already traveled to 3, so I'll be marking X here. I'll be traveling to 7. From 7 I have 1 and 8, so I'll go on with the 1, and 8 will not give the solution. So this is one of the another solution. Now next possibility is from 1 to 2. From 1 to 2, I have two options: either to 8 or to 3. Okay, 8 or to 3. 8 will give the dead end, so I'll mark a cross here. Then from 2 to 3, well, when I go to 3, I have from 2 to 3, I can directly go to 1, or I can go to 4, or I can go to 6. Okay, so if I go to 1 directly, that's a valid solution, or if I go to 4, or I can go to 6. Okay, now this is done. 4 and 6. From 4 I can go to 5, then to 6, since only one possibility. From here I can go to 3 or to 7. If I go with 3, it's repeated, so I can't take it. I'll go to 7, and from 7 I can go to 1 or 8. Okay, 1 will give the solution, 8 will not. In the same way, we'll continue for all of those. Like for example 6, we can go to 3 or 7. 3 will not give the solution, and 7 will give the solution through 1. Okay, 8 will not give the solution. Coming to 7, 1 to 7, I have two options, 8 or 6. Okay, if I go to see, if I go to 8, it will be stopped. If I go to 6, then I have a possibility. I can go to 3 or 5. Okay, so see here, 3 or 5. If I go with 3, I can go to 4, 1 or 2. So if I go with 1, it's all right. If I go with 4, or I have option with 2 also. So if I go with 2 here, 2 to 8 and 2 to 1. So 2 to 8 is not possible, 2 to 1 is possible. And from 4, I can go to 5. From 5, 6. Then from 6 to, I have two options, 3 or 7. 3 is already repeated. 3 is repeated, so I can't take it. I'll go with 7. And from 7, where I can go? From 7, I can go to 1 or 8. Through 1, I'll get the answer. So I'll go with 1. Okay. And coming back, we have from 2. From 2, either I can go to 1, it's done. And here it is, here 5. From 1765, 1765. Then 5 to 4, 4 to 3. Then from 3, I have two options, either from 2 or from directly to 1. Okay, so I'll go directly with 1 first, or I can go from 2 to 1. Okay, so these are all the possible solutions where all I have marked the tick. That are all the possible Hamiltonian cycles. Okay, coming to graph coloring problem, see here, its application is in the maps. So this is a map here. So there are many different parts of the map, and we can map, and what we have to do is, while printing this map, we have to assign each of these states different color, right? We can't assign two adjacent states same color, then it will be confusing. Then there will be confusion, what is the actual area of this state and what is the actual area of this state. Okay, so for that purpose, what we'll be doing, we'll be assigning different colors to every territory. So for two adjacent territories, we can't assign the same color, so in that, the graph coloring used. Okay, so how can we convert this map into a graph? Mark this territory as 1, and this has 2, this has 3, this has 4, and this has 5. And after that, see here, these two have the same border here, so make a edge between those two nodes, and these two have the same border. The sharing borders will be having the edge between them. Okay, and 2 and 4 will be marked here, and 5 and 1, 3 and 4, 4 and 5, 3 and 1. Okay, now after we get a map like this, like graphs, the nodes and the edges, then we will be writing the nodes and the edges here, 1, 2, 5, 4, 3. Now see here, we have the edges here, we have the nodes here, we'll be marking the edges. So edges are as follows. Now see, we have the graph here. Now by using this, what we can do is, we can find out if the two adjacent nodes have the same color or not. Okay, so in this question, in exam you can expect this type of question. Draw the portion of the state space tree for m colorings of a graph when n is equal to 4 and m is equal to 3. Now what is n, what is m, and what we have to do here, let's discuss about that. N is equal to 4 means there are 4 nodes. Okay, so let's take for our any 4 nodes you can take. I'll taking 1, 2, 3 and 4. Now m is equal to 3, so we can take any graph, for example. Okay, since they have not specified which type of graph. N is equal to 4 and m is equal to 3. Okay, so m is equal to 3 means I can take 3 colors. I'll be taking red, green and blue. Okay, now what we have to do is assign for each node either red, green or blue. So suppose that if I assign here red, then if I have to change here, I cannot assign this and this to red because this is already red. Okay, so if this is red here, I can't make it red because its adjacent node should not be the same color. Okay, so I can assign here green or blue, right? Either green or blue, and same thing with here also, green or blue. In case if I select green here, I cannot assign green to this, but I can assign red to this. Okay, because red is not adjacent to this one and this one also. So in that way, how many possible combinations are there, that we will be finding out. Okay, so the first thing what you have to do is make the root node here. and then we have the first node here. Okay, we'll be taking the first node. In the first node we can take either red, or the first node can be green, or the first node can be blue. All right, so the first node is red. If I have taken, the second node cannot be red, so either it can be green or it can be blue. Okay, so first node is red, it's connected to the second node, it can be either green or blue. Now in case it is green, then it is connected to the third node, which can be either red or blue. See here, the second node, if it is green, this is red, this is green, so in our case it is like this: red, then here green, then the third node can be red or blue. It can be red because this is red, but this is not adjacent to 3, so this can be red here, and it can be blue also because no adjacent node has blue to it. Okay, then 3 is connected to 4, so we'll connect 3 to 4, and when we connect to 4 we'll have just one possibility. Why? See, this is red here. Okay, we can have green or blue, but we have to see the connection from 4 to 1 also. See, when we connect this one to this, we are checking for this, it should not be the same color of this one, but also we have to see it should not be the same color of this one also. So this is red, so it cannot be red here. Okay, so in this case, since 3 is red here, this will not be red anyways, so we can have two possibilities: green and blue. The same thing for here also. 1 is red, 2 is green, 3 is blue, and from here we'll have fourth node. Fourth node cannot be blue because this is adjacent to it, and fourth node cannot be red because it is adjacent to it. So fourth node can only be green. See here, in this case only one possibility is there: green. Okay, so let's fill this one also. In here, red and blue, red, blue, and this is connected with 3. Now 3 can have two possibilities, either green or red. So in case if it is red here, then um, if it is red, then 4 can be either green or blue. Okay, see here, if it is red here, then 4 can be either green or blue. Since both of these adjacent vertex have same color, this can have either green or blue. That's one possibility. The second possibility is green here. 3 is green. If this is green, at that time it the fourth node should not be green and should not be red. So only one possibility. In case it if 3 is green, then 4 will be only blue. Okay, like that we have to fill for the remaining also. Okay, so this is the second possibility of the colors, and the third possibility I have not made here because the space is not enough, but in exam time we have to make the whole graph. Okay, so in that way we have to select the space so that all the graph can be fit in the same place. Okay, so by using this, these are all the possible color combinations which we can take. So by using this we can assign the colors, like first node is red, so we will be assigning the red to the first color. Second one is green, so second one will be green here. Third one is red, and fourth one is blue. Okay, so fourth one will be given here blue or green, both can be assigned. Okay, so fourth one will be either blue or green. So by using this node numbers here, we'll be using the same node numbers in the map also. Okay, see here, first node was this, so whatever the color combination we get here for all the nodes, that one will be applying in this map. So we can get a variety of combinations in which the adjacent two states will not have the same color. Okay, under program and bound, the first one is job assignment problem. So the question will be of this type: apply branch and bound technique to the following assignment problem. Okay, so we have been given with a matrix where we have the persons like this P1. Okay, I'll mention it: P1, P2, P3, P4, and these are the jobs. Okay, so what the thing is, each person can do only one job. Okay, these are the jobs, and these are the cost which the person will take to do the job. Okay, and person 2's jobs cost, and person 3's jobs cost, and person 4's jobs cost. Okay, so you have to assign all the jobs to all the persons, and we have to do that with minimization of the cost. Okay, so firstly what we'll do is we'll do this in many steps. So firstly we'll select the minimum among this one, which is 2. and minimum here it is 3, and minimum here it is 1, and minimum here it is 4. After writing that, find out the minimum and write here. That will be lower bound. Okay, lower bound is 2 plus 3 plus 1 plus 4, which is 10. Okay, after writing this, we'll be seeing if it's possible or not. It's not possible because P2 and P3 are getting the same jobs. Okay, and job 1 is no one is getting. So this solution is not possible. So let's start the sequence of steps. Firstly, we'll be selecting the um, P1 J1. Okay, see, we'll be starting from person 1. We'll be assigning the jobs to the person 1 first. Okay, then we'll be moving on to person 2, then to person 3, and then to person 4. Okay, see here, person 1 can be assigned with the job 1, job 2, job 3, or job 4. So I have 4 possibilities here: P1 J1, person 1 with job 1, and person 1 with job 2, person 1 with job 3, and person 1 with job 4. Okay, there are 4 possibilities. Now by using these possibilities, we'll be calculating the cost for each of these. If person 1 is given the job 1, what you do, you select it as like this, and then mark a cross here. Okay, since job 1 is given to person 1, other persons can't perform, and then the second thing, person 1 cannot perform other jobs. So these are the eliminated options. You have to select the minimum among this one: 4, 3, or 7, 3, 8, 1, or 8, 1, 6, 9, or 4, 4. Then write 9 plus 3 plus 1 plus 4. Okay, 9 plus 3 plus 1 plus 4. Keep it like this. Second one, P1 J2. Erase this. In the second option, we are selecting job 2 for the person 1. Then cut out the row and the column. Then select the minimum: 6, 3, or 7, 3, 5, 1, or 8, 1, 7, 9, or 4, 4. 2 plus 3 plus 1 plus 4. Right here, 2 plus 3 plus 1 plus 4. Okay, then third one, assigning job 3 to person 1. So when we assign job 3 to person 1, 7, cut out the row and the column. 4, 6, 4, or 7, 4, 5 or 8, 5, 7, 6, or 4, 4, 7 plus 4 plus 5 plus 4, 7 plus 4 plus 5 plus 4. P1 to J4, the person 1 is given job 4. Cut out the row and the column. 6, 4, or 3, 3, 5, 8, or 1, 1, 7, 6, or 9, 6. Then the sequence is 8 plus 3 plus 1 plus 6, 8 plus 3 plus 1 plus 6. Add up these: 9, 10, 11, 12, 12 plus 5, 17, 5, 2 plus 3, 5, 5 plus 5, 10, 7 plus 4, 11, 11 plus 9, 20, 8, 9, 10, 11, 11 plus 7, 18. Select the minimum, this one. From where we got this one? P1 J2 means assigning this job will get the minimum cost. So then the next step is you have to block this job to P1. So this job is selected for P1. Okay, when you have selected any job, at that time the other jobs cannot be performed by the person, and the same job cannot be performed by other persons. So we'll be cancelling out these options from our um, set of options. Okay, so P1's selection is over. He will be performing job 2. So since P1 is performing job 2, we have to now focus on P2. P2 can perform either 6, 3, or 7. So three possibilities: P2J1, second possibility is P2J3, and third possibility is P2J4. Okay, so this you mark it as X here. So now we'll be focusing on these three possibilities. In all of these, 2 will be the first one, means since 2 is assigned, the total sum will be starting from 2 plus. Okay, here also 2 plus, and here also 2 plus. Now see here, if it performs the job 1 is given to person 2, at that time the row and the column will be eliminated, and remaining one is 1 or 8, 1. 9 or 4, 4. 6 plus 1 plus 4. Right here, 6 plus 1 plus 4. Then the next one is P2 J3. P2 job 3. Okay. So select 3 here, eliminate the row and the column. 5 or 8, 5. 7 or 4, 4. 3 plus 5 plus 4. Okay. Right here, 3 plus 5 plus 4. Then the third one, which is P2 J2. P2 J4. That means this one, 7. When we select 7 here, the row and the column will be eliminated. The remaining one is 5 or 1, 1. 7 or 9, 7. 7 plus 1 plus 7, and here we had 2, so 7 plus 1 plus 7. Okay, so these are the three options here which we got. Now calculate the sum. 6 plus 2 12, 6 plus 2 8, 8 9 10 11 12 13. 5 9, 9 plus 5 for 14, 7 8 9 10 17. The minimum is this one. Okay, so we'll be selecting P2 J1. P2 J1. This one will be selected for P2. This will be selected for P2. Okay, this will be blocked. And so for P2 it is over. Now for P3. P3 we can select 1 or 8. So for this one will be selecting, we can go with, see, 2 plus 6 is already there. So 2 plus 6 plus, and here and this one is P3 J3, and this is P3 J4. Here I can go with 8. So 2 plus 6 plus, and now we will solve the problem. If I select 1 here, the row and the column will be eliminated and will be remaining with 4. So 1 plus 4. And the next one, is um, selecting 8. If I select 8, the row and the column will be eliminated. Remaining one is 9. 8 plus 9. 8 plus 9. Now we'll be calculating the sum. 6, 7, 8, 9, 10, 11, 12, 13. 13, and from here 6, 7, 8, 8 plus 8, 16, 16 plus 9, 25. Now this minimum, so we'll be selecting this one. This means P3 J3. Block the job 3 for person 3. Okay, so when we block the job 3 for person 3, we'll have this done and this also done. So the remaining job is 4, so we'll be selecting that for P4. Okay, so P3 and P4 both are done, and job 4 is P4. So here P4 J4, which is 2 plus 6 plus 1 plus 4, and the minimum cost is 13. Okay, so this is the job assignment problem using branch and bound technique, and the jobs assigned are P1 J2. So these are the jobs assigned. For this one it is for the first one it is P1 J2, and the second one it is P2 J1, and the third one it is P3 J3, and the fourth one it is P4 J4. Okay, these are the 4 jobs assigned. So let's erase the rest of the things. So finally in the answer script you have to show like this. Okay, and along with these things, means how you reach the conclusion. Okay, this is the traveling salesman problem, and the question is, apply the branch and bound algorithm to solve the traveling salesman problem for the graph below. In this graph we have 5 nodes, A, B, C, D and E. Okay, and the cost edges are also given to us. Now to solve this problem, first let's discuss what is traveling salesman's problem. If you start from any vertex, in this case we'll be considering A as the source. You have to travel to each the vertex and return to A. Okay, like for example, A to B, B to C, C to D, D to E and E to A. In that way many possible combinations are there, and you have to select the combination from among those combinations which will give us the least cost. Okay, so the cost will be from if I travel from A to B, the cost will be 3. Then from if I travel from B to C, it will be 3 plus 6, like that, plus 4 plus 3, like that. Okay, so many combinations are there. We have to find out the least cost one. Okay, so first what we'll be doing, observe carefully. Since A is the source vertex, I'll be taking first A, and now C. In A's connection, this is there, this is there, this is there, and this is there. What are these numbers? 8, 1, 5, and 3. The least two is 1 and 3, right? So what I'll be writing here is LB, that is lower bound, is equal to 1 plus 3. 1 plus 3. Okay. Then in the same way, select for the next one, which is B. Selecting B, the edges are this one, this one, this one, and this one. The costs are 3, 6, 7, and 9. The least two are 3 and 6. So I'll be writing here plus 3 and 6. Okay. Then select the next one, which is C. In C, the edges are this one, this one, this one, and this one. The least two are 1 and 2. So I'll be writing here plus 1 plus 2 plus the next one is D. Selecting D here, the edges are this one, this one, this one, and this one. The least two are 3 and 4. So I'll be writing here plus 3 plus 4. The last one is E. For E, what we have, the edges this one, this one, this one, and this one, 2 and 3. So I'll be writing here 2 plus 3. Then the whole divided by 2. When you do this, we will get the answer as 16. Sorry, not 16, it's 14. Okay, so we get the answer here as 14. Now this is the first step which we have to do, finding LB. Okay, so what I'll be doing is, I'll be writing here, since we started from the source vertex A, I'll be writing here A, and below that I'll be writing least bound is equal to 14. Okay, so this is the first step. In second step, I'll be solving in other paper because there are many calculations needed. So here I'll be just maintaining for the state space tree. Okay, so next what we'll be doing, see here, for each of these, now I'll be selecting, see, we got the minimum one from A. Next we have to select A and B. Okay, A and B. Then we'll be selecting A and D. Then we'll be selecting A and C. Then finally we'll be selecting A and E. Okay, so when we select A and B, then again we'll do the same thing. From A, what are the edges from A? This one, this one, and this one, and this one. Now when we have highlighted one, then we have to select that compulsorily. Okay, so this one is selected. So from among these, what's the minimum? 8, 1, or 5? 1. So the edges which we have are 1 and 3. For that I'll be writing here LB is equal to, this is for A comma B. Okay, this one was for A only. Okay, this for A comma B. LB is equal to 1 plus 3. Okay, then for the next one, select B. From B, how many edges we have? This one, this one, this one, and this one. This is already selected, so we have to select the least from among these three, which is 6 here. So we'll be writing 3 plus 6. Then select the third one, which is C. Selecting C, the edges are 1, 6, 4, 2. The least two are 1 and 2. Okay, so actually what we have to do, we have selected this edge, right? So since C is not directly connected to this, we have to select those edges through which C will be through which the selected edge will be coming. Okay, so suppose that if I select 1 here, at that time I should make sure that if I select this one, it will go through this edge and come back to C. Okay, next if I select 2 here, from C I should be able to go indirectly towards this edge and come back to C. Okay, in some way. So if that's possible, then only I'll be selecting the minimum two edges. So suppose that one goes through C like this, one goes through the selected edge and comes back to C, but the next minimum, which is 2, it does not go. Suppose that this edge was there but this edge was not there, in that case it will not be possible to travel to this edge. In that case I cannot select 2, instead I will be selecting 4, okay, because it goes through this edge here, okay. So in that case we have to calculate, but since in this problem that's not the case, because all the vertices are connected to all the other vertices, okay. So we'll be just looking at the minimum edges here, okay. In this case, since this is not directly connected, we'll be looking at the two minimum edges, which is 1 and 2. So I'll be writing here plus 1 and 2. Then C is over. Next one is D. D is also not directly connected, so we'll be selecting the minimum edges from among the edges of D, 4 and 3, plus 4 plus 3, and E also is the same thing, 2 and 3, and this whole divided by 2. This answer we'll get as 14, same as the previous one, okay. So this was for AB, okay. The selected edge was AB. The next possibility is AC, okay. AC. For AC, let's see how to do that. For AC, LB will be equal to, first one is from A. From A, this one edge is already selected. Then the next one is among 8, 5 and 3. The minimum is 3. So these two are selected, 1 plus 3. Plus B. From B, it's not directly connected. The least two are 3 and 6. From C, this is selected. The second least is 2. Then from D it's not directly connected. The least two are 4 and 3. From E it is 2 and 3. And we will be calculating this and divide by 2. We will get the answer as 14. Then from A to D, we will be selecting this edge. From A, this is selected, so we have to select the minimum among 1, 8 and 3. This minimum, so the selected edges are 1 and 5. I'll be writing here LB is equal to LB is equal to 1 plus 5. Then from B it's not directly connected, so 3 and 6. From C also it's not directly connected, so 1 and 2. From D it is 5 is selected, so the remaining edges are 7, 4 and 3. The minimum is 3, so we'll be selecting 5 and 3, plus 5 plus 3, plus from E it is not directly connected, so it will be 2 plus 3, and this answer divided by 2. This will get as 16. Okay. Now since we got from A to D, let's find out about A to E. This is the last one from the source vertex A. This one will be selected. Then from A, what all options we have? From A this is selected, so we have to choose the least among 1, 5 and 3. The least is 1, so these two are selected. We'll be writing LB is equal to 1 plus 8. Since B is not directly connected, we'll be writing 3 plus 6, and C is not directly connected, 1 plus 2, and D 4 plus 3. Coming to E, what we have is this selected, so we'll have to select 8. Then the least among 2, 3 and 9, it's 2, so 8 and 2, plus 8 plus 2 divided by 2. For A to E, we'll get the answer as 19. So these are all the possibilities which we have, these 4 possibilities. Okay, these are the 4 possibilities: A to B, A to C, A to D and A to E. This will be making in this table from A. Okay, from A what all possibilities we have? See here, A to B, A to C, A to D, A to E, and the least bond among these 4 are from A to B. What we got? 14. From A to C, what we got? 14. From A to D, 16. From A to E, 19. So see here, the thing is what we'll be doing now. Two answers we got same. We have to select the one among these two. It's not necessary to select one among these two. We can move on further with calculating both of the values. But since this problem is already solved, the thing is, if you find out the solution for both of these, we'll get the same answer at the end, because this is just a change in the sequence. Okay, this I can say because I've solved the problem before. So to avoid solving the repeated same solution again, I'll be mentioning the thing which is happening in this case. But we cannot always find out if you get the same answer here. It can cause different answers at the end also, but in this case it will cause the same answer. Okay, this actually what happens is, from A B we get the answer as like this: A to B, B to D, D to C, C to A, or A to C, C to D, D to B, B to A. So in this case, what happens is, it will be in this way. If I travel from A to B, A comma B, A comma B, then D, then C, then A. If I travel from A to C, it will come as A, C, D, B, and A. Okay. So the cost will be same in both of these cases. So you can select either one of these. Okay. But you can't do that in exam, because we don't know if this will lead to the same loop or not. Okay, there can come different loop also, but since this question is solved earlier also, so I know that it will come the same answer. So for this part I'm skipping. Okay, so we can't skip in exam. Okay, we have to find out. Okay, so for the explanation purpose, I am and that for the time constraint, I am going on with this solution. But it doesn't mean that if we get the same answer, we have to choose either one of these. Okay, we have to solve both of these, even if we get the same answer. Okay, so let's select the minimum one, which is this one. Okay, see, we had two minimum here. From among this, due to time constraint, I am selecting this one, AB. Okay, now see here, when we select AB, we have to select this edge here. Okay, this selected edge. Now we have three possibilities now. From B I can travel to C, from B to D, or B to E. Okay, I have three possibilities now. We will be looking at three possibilities one by one. We'll have to include the, in the first case I'll be going on with A, B, B to C. Okay, so A, B, B to C. Okay, the least bound is for A. From A, what we have, see here, first if we select this row here, if we select this edge here, A to B, B to C. Okay, from A we have 3, and the next list is among 8, 1 and 5. Okay, so we can select this one. So 3 plus 1 we'll write here, 1 plus 3. Then plus, from B, from B we have to select the minimum edges among these 4. Since these two are compulsory, I will have to select these two. Okay, then coming to the node C, we have to select the minimum among 1, 6, 4 and 2. Since this is compulsory, we have to select 6 here, and the remaining ones are 1, 4 and 2. The minimum is 1. So the selected nodes are 1 and 6. So I'll be writing here plus 1 plus 6. Then from for D, there is no compulsory edge here. So I'll be selecting the least 2, which is 4 and 3. Same thing for E also, it will be 2 plus 3. And calculating this and dividing by 2, we'll get as 16. Okay, and next the same thing we'll be doing for A, B, D. Okay, this one was for A, B, C. A, B will be constant here because it's selected here. We'll be just changing the from B where we are traveling to D. Okay, A, B, D. Now see, to A, B, D. From A we have to select 2. 3 is compulsory, so the next least among 8, 1 and 5 is 1. So it will be 1 plus 3, plus from B it is 2 compulsory here, 3 plus 7. From C it is no, there is no compulsory edge here, so we'll be selecting 1 and 2, plus 1 plus 2, plus from D it is the 1 compulsory edge 7, and the least among 5, 4 and 3 is 3, so 7 plus 3. plus the last one E, which is 2 plus 3. That will give us the answer, and dividing this by 2, we'll get the answer as 16. Okay, this for ABD. Then the next one is ABE. From A it is 1 and 3. Okay, we'll be writing here ABE. From A it is 1 and 3. 1 plus 3 plus, and B it is 3 and 9. 3 plus 9 plus. Then from C it is 1 and 2 plus the next one, which is D. D is 4 plus 3 plus 2 plus 3. This dividing by 2, we'll get the answer as 19. Okay, this for ABE. So let's observe the values which we got here. See, these are the three values which we calculated: 16, 16 and 19. So let's make the tree here. This selected one. So from here we'll be having three possibilities: A, B, C. The next one is A, B, D. The third one is um, A, B, E. All right. So we have these three. We'll be filling in the values 16, 16 and 19. Okay. These three values. Now the minimum is these two, but in this case we have to select both of these. Okay, because it will give us the different answer. As I told you before, selecting this one was because I already know the answer, that this will give the same loop, but we can't decide on the basis of the same answer, because in this case it will give the different answer. Let's see that. So we have to select both of these now. Okay, selecting both of these, what all possibilities I have. First, let's discuss about ABC. ABC is selected now. Okay, ABC is selected, and then from C, what all possibilities we have. From C, I can travel to D or to E. Okay, I have two possibilities now, from A, B, C, then D or E. A, B, C, then first case I'll select as D. Now see here, observe carefully. If I select this path A, B, C, D, okay, then the only possibility which I have is traveling to E. From D I can travel only to E, right? Because I have to travel to E then to A, because all the nodes are to be selected. I can't directly travel to A, E will be missed. I can't travel back to C, and I can't travel to B because it will be repeated. So only option I have is to E. Okay. Once you get the four nodes here, if there are total 5 nodes, then you can directly go with this solution. Okay. Means what is the possibility left? You can go with that. Okay. Now, what are the sum of the edges that will be writing here? A to B is 3. 3 plus 6 plus 4 plus 3 plus 8. Okay, so this will give us the answer 24. Okay, so in the same way we'll be doing for the next one, which is A, B, C. Then we'll be not going with D, but we'll be going with A, B, C, and then E. Okay, if I go with E at that time, I can either go to A or I can go to D then A. Since if I go directly to A, I'll be missing out D, so I have to go through this path. Okay, so the sum of the edges will be 3 plus 6 plus 2 for the path through E. It will be A, B, C, E, and then D. Okay, so here it will be 3 plus 6 plus 2 plus 3 plus, then till A it is 5. So calculating this sum, we'll get the answer as 19. Okay, this was for the path through E. Okay, so these two answers which you got here, those are nothing but the combination A B C, then D, A B C, then to D or to E. Okay, so you got the answers as 24 and 19. That will be mentioning here. Okay, in the state space tree. Okay, for this one, if I go with A B C D, then I'll get the answer as the first one, which is 24. Okay, and if I go with A B C and E, then I'll be getting then I'll get the answer as 19. This was for ABC. Now let's look at the second possibility, ABD. Okay, so what I'll be doing is I'll be erasing the edge from B to C, and I'll be selecting the edge from B to D. Selecting this edge A, B, D, then I have two possibilities. Either I can go to C or I can go to E. Okay, so we'll be looking each possibility one by one. So in the first case, if I select C, the cost of the edges will be from A to B, then B to C, A to B, B to D, then D to C, then I have only one possibility left, going to E, then to A. Okay, so the cost of the edges in the case A, B, D, C, E. Okay, in this case, the sum of the edges will be 3 plus 7 plus 4 plus 2 plus till A it is 8. Okay, so calculating this, we'll get the answer as 24. Okay, and the next one, which is ABD, then ECA. This is the second possibility, right? E, then C, then A. So in this case, the cost will be A, B, D, E, C, and then A. A to B, 3 plus 7 plus 3 plus 2 plus 1. In this case, we will get the answer as 16. We got the four answers now. We'll be noting down the second two values which you got, 24 and 16. From here, two possibilities are there. A, B, D. See here. A, B, D. First one we took as C, E, A. Okay. D, C, E. Okay. In this case, what's the answer we got? We got the answer as 24. In the second one, which is A, B, D, E, C, A. A, B, D, E, C, A. Okay. This answer we got as 16. So comparing this four, what's the least one? 16. So this is the optimal tour for the salesperson. Okay. So finally, we'll be writing the um, answer here, which is the minimum tour. So which path he should take? A, B, D, E, C, A. A, B, D, E, C, A. So the cost will be from A to B it is 3, from B to D 7, which is 10 here, then D to E 3, 13, E to C 2, 15, and C to A 1, 16. So minimum cost is 16. Okay, and this is the optimal tool for the given problem. Under the knapsack problem, we have three types. First one is normal, second is LC, and the third one is FIFO. Okay, so we'll be discussing the first one, which is normal branch and bound technique. So in this, the type of the question which you can expect is solve the following instance of knapsack problem using branch and bound technique. If they don't mention anything like it's LC or it's FIFO, at that time you can go with the normal method. Okay, so here's the problem. Given knapsack capacity is 10, so W is 10. And if you don't remember what is knapsack problem, see here we will be given with some items here. So the item numbers are 1, 2, 3, and 4. So the weights of each item are like 4 kilogram, 7, 5, and 3. Okay, so we have been given with a capacity 10 here. So the container is of 10 kilogram. Okay, so we have to include the items here. We can include this item, this one and this one. Okay, so if we include all the items, it will exceed the value 10. So we have to select some items now. So while selecting which item should be selected, that will be uh, finding out using knapsack problem. Okay, either we can select the item or not select the item. If we select, we have to include the whole item, which is 4 kilogram. We can't do the fraction here. Okay, it's 10 knapsack problem. Okay, in backtracking in module 5 we'll be using 10 knapsack problem in the greedy method, which we had done discussed earlier, or maybe it was dynamic programming, but there we had included fractions. Okay, so that means if the capacity is 9 here, 9 kilogram, at that time only 1 kilogram is left, but we have item 4 of 3 kilogram. At that time we can divide this into 3 parts and include one third of it. Okay, but here we'll not be doing that. If it's 9 kilogram and the remaining item is this one, we'll not be including it. Okay, so let's get started with the first one. See here, initially what you have to do is divide the value by the weight. Okay, so see here, it's consider this as mangoes. Okay, you have 4 kilogram of mangoes. Okay, 4 kilogram of mangoes. Now what we have to do is, the value is 40, means the price is 40. Okay, $40. Now I need a price for 1 kilogram. What I will do, I'll divide 40 by 4, then I'll get the price of 1 kilogram as $10, right? That I'll be mentioning here. I'll be finding out the value of, means the price for 1 kilogram of each object. Okay, so I'll be dividing the value with the weights. Okay, then I'll be getting the value for 1 kilogram. I'll be arranging that in the descending order. This is already in the descending order: 10, 6, 5 and 4. Now we'll move on to the problem. The first step what you have to do is make this box here and write a 0 here. This is the root node. In root node we'll have two variables here. If you observe carefully, we have W and V. Initially we don't have any weight, means we have not included any object, so W is 0 and value is also 0, since no object is included. Okay, so then what we have to do, we have two options. We'll move on in the from object 1 to object 4. Okay, so initially we can include item 1 or not include item 1. So there are two possibilities. For the root node, we can either include the item 1 or exclude the item 1. So in these two possibilities, before that we have to find out a value called upper bound. Okay, how to find the value of upper bound? This is the formula for upper bound. Upper bound is equal to V. In our case, see here, let's note down what is V and W. It's see here, there are two W. The capital W is the capacity, which is given as 10, and the small w is 0 because we have not included any object, and value is also 0 because the profit is 0 here. Okay, we have not included any object, that's why value is 0. Now using these three values, we'll be substituting in the this equation. So what we get is, when we substitute V as 0 here, we'll write here as 0. First one we are finding for the root. Okay, root upper bound, 0 plus the total weight is 10 minus the initial weight is 0. So 10 minus 0 into 10. What is this? This is Vi plus 1 divided by Wi plus 1. This is nothing but the weight by value by weight ratio of the next object. Okay, so I'll be telling you why we are doing this using this formula. See here, the after the root node, the next object is 1. Okay, so the value by weight ratio of the first object is 10. So we will be writing here into 10. Okay, so see here, what we are doing actually is, we are calculating how much maximum profit we can get by including the object 1. In object 1, we have the profit for the 1 kilogram as 10. Okay, suppose that the whole capacity of 10 kilogram is filled by the object 1. Although it's not possible, we are just finding the upper bound here. So we are assuming that we have the sufficient weight, means 10 kilogram we have. In that case, how much profit can I get? For 10 kilogram, I'll get the profit as 10 into 10, which is 100. Okay, so that's the same thing which we are doing here, 100. Okay, how we got that? V is the initial profit. If we have any initial profit, that will be adding it. If you don't have, we'll be writing 0. And how much weight is left, means how much weight is used and how much was the total weight. So if you have used any object, that weight we have to deduct, right? So it will be how much weight we have into what is the profit for 1 kilogram of the next item. So if 1 kilogram is 10, and how much weight I have, that I'll multiply, means if I have 5 kilogram left, I'll be getting the maximum profit possible. Okay, that is the upper bound, and this upper bound will be written here. Okay, this very important step, we'll write the upper bound here. We got as 100. Okay, this will be written here. Next, what we have to do is we have two possibilities, either include object 1 or exclude object 1. In case we include object 1, what will be the weight? Weight is 0 initially. If we include object 1, what is the weight of object 1? It's 4. So it will be W is equal to 0 plus 4. That will be 4. What will be V? V is initially 0. 0 plus what's the value of this one? 40. So V will be 40. W is 4 and V is 40. Okay, that will be writing here W as 4 and V as 40 in case if we include object 1. The second possibility is not including object 1. If you don't include object 1, weight and value will be same here. Okay, then we will find out the upper bound for each of these case. Now we have the updated values, small w as 4 and V as 40. Okay, so let's update the values here. W is 4, V is 40. Now if we use these values in the main equation, here I will be writing 40 plus capital W is 10, 10 minus how much is used? 4. So we have 6 kilograms left, and here V value is 40, 40. 6 into what is the weight, what is the value and weight ratio of the next object? Okay, 6 into that value here, that we get as 6. Okay, see here, the value weight ratio of the next object is 6. So what we are doing is, since we have included object 1, the total remaining weight in the container is 4 is already used, 6 kilogram left. Okay, if we include 6 kilogram of the object 2, what will be the price we get? That can be found out by 6 into means how much kg is left into price for 1 kg. Price for 1 kg is 6 and weight left is 6. So 6 into 6 is 36. I can get $36 profit by including the whole means how much value is left by the item 2. Okay, so I'll get as 36, and initially I got the profit as 40 by including object 1. So 40 plus 36 will give me the maximum profit possible by including object 2. Okay, so that will be writing here 40 plus 10 minus 4, 6 into 6. Okay, that I'll get 36 plus 40, 76. So 76 I'll be noting down here. Okay, this is 76. All right, then without including object 1, what is the way this one upper bound? In upper bound, what we'll be doing is, see, we have not included object 1. Okay, we have not included object 1, so this weight is not used. So still we have 10 kilograms left. So what we'll be doing is, the whole 10 kilogram will be filling with the object 2. Okay, so if you fill that whole 10 kilogram with object 2, what is the profit? For 1 kilogram profit I'll get as 6. For 10 kilogram I'll get as 60. So here I'll be writing 60. If you observe the formula, in the formula also we'll be doing the same thing only. See how much value we had initially. Since we are not included object 1, the value was 0, and how much weight is left? 10 minus 0, we have 10 kilograms still left, into what is the value weight ratio of the next object? It's 6. So 10 into 6 is 60. So the maximum profit I can get by including the object 2 in the whole container is 60. Okay, see, one decision what we can make is, we have two possibilities now. Since we have to maximize the profit, we'll be going on we'll be choosing the maximum one, but that doesn't mean that this is eliminated. This is not eliminated. Okay, we have still possibility that this profit is just giving the maximum possibility, but this can be ended up with like 40. Okay, this can come to be 40 and this can be 60 only. If we expand it further, then this one will be selected and this one will be rejected. So what we have to do is, at this point of time, we'll keep it as empty here, we'll not do anything, we'll move on with the this one, and then we will see if we get any more answer than this in the lower part, then we can exclude this one. Okay, that will be understanding when we actually solve the problem. Okay, so for now we'll be selecting 76 and moving on with the object 3. In object 3, if we include, what will be the total weight? We have included object 1 and then we have included object 2 also. Okay, now we are including object 2. Okay, not object 3, we are including object 2 because at this point we had included object 1 and then selected among these two. Now we are including object 2 or excluding object 2. Okay, if we include object 2, what will be the cost? Here I will get weight as 7. So initially weight I have 4 here from the object 1 plus 7, which is 11. See here, total weight, if I select 2 and 1, I'll get total weight as 11. That's exceeding the capacity of the container, which is 10. It's just 10. We can't include 11. Okay, so we'll not be going on with the selection of 2. Okay, so in case if we don't select 2, then what's the case here? See here, weight is already exceeded, so we can cross out this possibility. Okay, this confirm here. Okay, so next one is this one, not including 2. See here, from 1 we are either including 2 or not including 2. Including 2 we didn't get the answer, so we'll exclude the 2 and see what's the possibility. If we exclude 2, we'll get the weight and value as same here, because we have not included 2 object. And what will be the upper bound? For upper bound, update the values. See here, weight is 4, v is 40. Okay, let's write here, weight is 4 and v is 40. Okay, for the next object, which is node 4, here the initial value is 40, so I'll be substituting 40 here, and 10 minus 4, since 4 is used, the remaining kilogram is 6 into the value weight ratio of the next object 3. Okay, since you are finding out for the object 2, no, not including object 2, that means the next possibility is including object 3. See, 1 2 3 4, we have not included object 2, so the next possibility is object 3. In that, the value weight ratio was 5. If you remember, it's 5 here, so we'll be multiplying with 5, means the next whole container, means 6 kilogram is left. 6 kilogram which is left, we are filling with the object 3, which has the value 5 for 1 kg. For 6 kg it will be 6 into 5 is 30. So 30 plus, this answer will get 30 plus 40. Initially from object 1 we have 40 here, 40 plus 30 will give 70. Okay, so we'll be filling in the node for 70. Here I can get the maximum profit as 70. Okay, then we have only one possibility now. This is excluded, so we'll be expanding this one. Now the task is for object 3. Now object 3 we can include or not include. Okay, two possibilities are there, either include or not include. We'll be drawing here two possibilities, either including object 3 or not including object 3. If we include object 3, the initial weight is 4 here, because we have not selected object 2, only object 1 weight is there, 4. Okay, 4. If we include object 3, the object 3 weight is 5 kilogram, so it will be 9. See here, object 3 weight is 5 kilogram, so we'll have the total weight as 9 kilogram. And what is the value? Initially I have 40 plus I'll get 25, which is 65, right? We'll have 65 now, the total value of the profit. Okay, 9 is possible because it's less than 10, the total capacity. W is 9 and V is 65. See here, W is 9 and V is 65. Okay, since we have included object 3, now we'll be using these values in the equation. 65 plus 10 minus 9, 9 is used, so 1 kilogram is left, into the ratio of the next object. Okay, it is 4. See here, it is 4. For 1 kilogram I'll get as 4, and I have only 1 kilogram left, which means 10 minus 9, 9 is used, so only 1 kilogram is left, and if I include that with this one, I'll get the total profit as 4. Now 4 plus the initial profit I had is 65. 65 plus 4 will give me the upper bound. Okay, that is 69. Okay, 69 is the total profit which I'll get by including object 4, by including object 4. Okay, in the next one. So see here, this will be 69. Okay, now the second possibility is not including object 3. If I don't this was see, till object 2 it was included, and I got if I include object 3 I can get 65, and then the upper bound will be 69. And here, without including object 3, what can I do? If I don't include object 3, that means this one is not included. The next possibility for finding out upper bound is including object 4. If I include object 4, what will be the total profit? See here, W is 4 and V is 40, so we'll be using that in the equation here. V is 40, initial profit, plus 10 minus 4 is 6 kilogram is left, into
the if I fill the next how much capacity is left with the fourth object, I'll get as 64. Okay, so in case I go with object 3 and then I try to fill with object 4, I'll get as 69. In case I don't go with object 3 and I go with directly with object 4, then I'll get the total profit here as 64. Okay, all right, and after this we have two options here, either go with this or this. This will give me the maximum profit of 64, but here I have more possibility, which is 69. So I'll go on with the object 3. Now moving on with the object 3, see, this is not excluded, still it can be expanded here, and maybe there's a possibility that I'll be remaining it at 64 here, and this can become like 40 and 50. At that time, this is the correct answer, so we'll just keep it here and it's not excluded. Okay, so the next possibility, after including object 3, I have two possibilities: include object 4 or exclude object 4. If I include object 4, the weight will exceed. See, only 1 kilogram I have, but object 4 is of 3 kilogram. Okay, see here, object 4 is of 3 kilogram. I have to include the whole object. So I can't go with that because the object will exceed the capacity. So I'll be excluding this one. Okay, the next one is not going with object 4. If I don't go with object 4, W and V will be remaining same, and the next object, there is no next object, so I have to just stop at 9 kilogram. 1 kilogram is not used. Okay, 1 kilogram is not used, and the weight and everything will be same. So if you see the formula, that will be the same thing here. The initial profit 65 plus 10 minus 9, 1 kilogram is left. Since I have no object left here, into 0, so this will not give any value here, and the remaining profit is the previous value 65. Okay, so here finally we'll get the answer as 65. Now we have to make some observations. See here, how many nodes are left? 1, 2, 3. 3 nodes are left. 3 nodes are left. We have to select the maximum among these 3. Now we have to not select the maximum among if it's 65, 64 or 60. You have to see some other parameter here. Observe carefully. To recap, V is the profit which I have in my hand, which is 65. Okay, 65 is the profit which I have in my hand. Okay, now this already I got. Then the next one is, what is the upper bound, means maximum profit what I can get. Maximum profit is 65 and I already got it. Okay, so if I follow this way, means if I include object 1, exclude object 2, include object 3, exclude object 4, that means 1 and 3 only I selected. At that time, I'll get definitely the profit 65. Okay, so this one thing I have to keep in mind. The next thing is, we will select the we'll observe the next node here. In this next node, this value gives me the total possible profit which I can get if I expand this. If I expand this, I'll get the total profit as 64, but already I have 65 which is guaranteed to me. So there is no point in expanding this one because it won't give me more than 64, while here I have guaranteed 65. I can exclude this one because it will give me anyway 64. I have more than 64 and it's guaranteed also here. Okay, then we'll see the next node here. Here the maximum profit I can get as 60. Okay, if I expand this one, I'll get the maximum as 60, not more than 60. But here I have already got here 65 which is guaranteed, so I can exclude this one as well. Okay, now if you observe, all the nodes are done. There is no node remaining, so the only remaining node here is this one. Okay, so this is the correct answer. Okay, and what's the sequence of steps which objects I have to include? I have to include object 1 and object 3. Now let's see, if I include object 1, the weight will be 4 and I'll get the value as 40. And if I include object 3, I'll get the weight as 5 and the profit as 25. So here the total kilogram is 9 and the total profit is 65. Observe here, the capacity is not full, but we have no other possibility also, because only 9 kilogram we can fill by using these two objects, and any other object will not fulfill the criteria of 1 kilogram. Either we have to include the whole object or we have to not include it. Okay, so this is the maximum profit which you can get in 1-0 knapsack problem. This is the second type of knapsack problem, which is using least cost branch bound LCBB technique. Solve the following knapsack problem given. Okay, So here n is equal to 4. N is nothing but the number of items here. Okay, so 4 items are given, and m is equal to 15 means, so the total capacity is 15. Suppose that this is a container, and we can fill in the objects, and the weights are given here. The total capacity of this container is 15. Okay, and by using this weights, we have to fill the objects. Okay, I can select any of the combination. Okay, when I select those combination, I have to fill here, and I'll get to know how much it is filled. It should not exceed 15. Okay, and which items I have to select, that's the main aim of this problem. Okay, we have to know which is the best selection among these. Okay, and the goal is to maximize the profit. These are the costs, means the first object's weight is 2 and its cost is 10. Okay, and the second's cost is 10, third's cost is 12, and the fourth's cost is 18. In this problem we'll be considering negative weights. Okay, so here it will be minus 10, minus 10, minus 12, and minus 12. Remember, branch and bound is minimization technique, so here we will be using negative weights. Okay, so the more negative we make it, the more minimized it will be, but in actual it will be more maximized. Suppose that I have two weights here, 20 and 40, which is greater here. It's 40 is greater, right? But according to branch and bound, we'll be finding, we can only find the minimum one. So in this case we will end up with 20, which is the wrong answer. So to avoid this, what we can do, we can make both as negative. Then in this case the negative one is minus 40, so branch and bond will select minus 40 instead of minus 20, and this is what we want. Okay, and finally we can remove the negative sign, but we'll get the correct answer at last. Okay, that's why we are making the signs here negative. Okay, so I'll be explaining you what all these things mean, so don't worry about these things. Let's get started with the solution. In solution, we are making nodes here. So we're making the state space tree, the node 1. Okay, and after that we'll be writing here u is equal to and c is equal to. Now let's discuss what is u and what is c. Okay, u means upper bound, c means lower bound. Okay, now see here, we'll be starting to consider the objects from item 1. If I include item 1 in this container, the first item will be 2 kilogram. What is the profit I get? Minus 10 right here. Then I can fill till 15, so I can allocate the second object here, which is 4. What's the profit? Minus 10. Third object 6, minus 12. How much it's total now? 6 plus 4 10, 10 plus 2 12, 15 I have, so 3 is remaining. 3 kilogram I can fill, but the fourth object is 9 kilogram here. Okay, this is 9. Okay, this is 9, and I cannot fill 9 here, so I have to fill out the fraction of 9 here. How much fraction? 3 by 9, because 3 only I can fill here. 3 by 9 I have to fill. Okay, 3 by 9 if I fill here, it will be 3 kilogram. And what will be the profit? 3 by 9 into the profit of the total 9, which is 6 here. So I'll be writing here minus 6. So total cost will calculate here and write here, that is minus 10, minus 10, minus 12, minus 6. That will be that will get as minus 38. Okay, so this is the lower bound. When you get minus 38, that's the lower bound. We'll be doing the same thing for upper bound also. In upper bound also we'll be seeing the same. First item here, it is 2, right here 2. What's the profit? Minus 10. Second object 4, profit is minus 10. Third object 6, profit is minus 10. The here and here only the difference that comes is we have 3 kilograms left here, but we cannot include 9 here because it's more than 3. So the second option is we can include fraction as this one, but here we will not be including fraction. This is the main difference between lower bound and upper bound. We'll be just stopping here. How much profit we got here, that much we'll be considering. It's minus 32. Okay, so the thing which you need to remember is in upper bound no fraction, and in lower bound fraction is there. Okay, so here upper and lower bound when we get, we'll be mentioning that here u as minus 32 and c as minus 38. We'll be solving more notes here, so you'll get a clear picture when we solve more examples. Okay, so for now just remember that ub means no fraction, lb means fraction, and we are starting from item 1. We are filling till we reach the end here. Okay, so let's solve for the node 2 here. This is the root node. Okay, then from here we can have two nodes, 2 and node 2 and node 3. Each will have u is equal to, c is equal to, u is equal to, c is equal to. this branch and bound technique, here we'll go with the BFS method, means breadth first search. So we'll be expanding 2 as these two nodes, 3 as these two nodes, then we'll be solving all simultaneously. In that way we are solving this type of problem, okay, under branch and bound. Next, for node 2, what we'll be considering is two possibilities: x1 is equal to 1, x1 is equal to 0. What is x1? See here, x1 is this, okay. That means if I write here x1 is equal to 1, that means I'll compulsorily have to include this weight 2. So here it will be compulsorily written as 2, okay. And x1 is equal to 0 means I'll not write here 2, okay. That the first object I'll be excluding, I'll be starting from 4, okay. So let's solve each case one by one. In the first case, I have to include compulsorily 1. First object is 2 here, so I'll be writing 2 here, and then the next object 4, the profits are minus 10 and minus 10, then 6 minus 12, and here I'll get the weight as 3, the fraction, and the profit as minus 6. So here total answer I'll get as minus 38, okay. And here in upper bound also 2 I have to compulsorily include, and 4, the next object here 4, and I still have the space left, so I'll be including 6 here, and minus 12, and further I can't include because the only space left is 3, but I have the object of 9. In upper bound we can't include fractions, so I'll be leaving the space empty here. The total profit will be noted down, which is 32. I'll be writing here 32. After we get C and U, note down in the state space tree, U is minus 32 and C is minus 38. Alright, we'll be doing the same thing for this one also. X1, in the first case we had included, now we'll be excluding X1. That means compulsorily we have to exclude X1. We'll not include this object. We'll be starting from 4. So when you start from 4, we'll be writing here first 4, and the total profit is minus 10. Then I'll be writing 6 here. The total profit is minus 12. 6 plus 4, 10, 15. 5 is left. So I can include 5 by 9 of 18. So if I include 5 by 9 of 18, I'll get as minus 10. Okay, so the total profit will be minus 32. Same thing we'll be doing here. 4 I have to 2 I have to compulsorily exclude. So I'll be starting from 4, then 6, and I can't include 9 in the space of 5, so I'll be stopping here. Then the total sum is minus 22. That's it. We'll be noting down U and C for this node. Here U I got as minus 22 and C I got as minus 32. Alright, now in this step we have to choose this one or this one. What's the rule? First we will be starting from lower bound. The lower bound for this one is minus 38, the lower bound for this one is minus 32. Which one is smaller? Minus 38 is smaller or minus 32 is smaller? This one is smaller. So kill this node here. Then expand from this node. Okay. And we'll be expanding this node. We'll be getting two possibilities: node 4 and node 5. We'll be writing U is equal to C is equal to U is equal to C is equal to. Now here x1 is over, means x1 has been selected. Okay. So we'll mark a tick here. Then we have to do for x2 now. So I have two possibilities: either x2 is equal to 1, means including x2, or x2 is equal to 0. Let's see which will give us the more profit. Okay, since x2 is included, we'll be marking a x2 space here, so we'll be writing x2 is included or not. Okay, so see here, the first possibility is x1 as 1, x2 as 1 for this one, node 4. Okay, so we'll be writing node number also here. Node 4 we are calculating. Okay, for node 4, for reaching node 4, x1 should be 1 and x2 should be 1. So we'll be marking x1 as 1 and x2 as 1. x1 and x2 as 1 means 2 and 4 should be compulsorily included. 2 and 4, minus 10, minus 10. Then here 6, minus 12. And here 3 is left, so I'll be writing here 3 and minus 6. The total sum is minus 38. Alright, and here 2 and 4 are compulsorily included, and 6 minus 12, and that's it. We can't include 9 in 3 here. Okay, so we'll be stopping here and noting down this value, and this is minus 32. Okay, so we'll be noting down the U and C values in the node 4. U is minus 32, C is minus 38. Come to the next node. In next node, one thing we have to change, x2 is 0 now. So we're making this one as 0. And this is node 5. Here the changes we have to make is x1 is 1 but x2 is 0. So the second we have to exclude. We have to not include the second object. If you don't include the second object, then what we have to include? If you don't include this one, the next possibility is this one. So we'll be including this one, 6. 2 plus 6, 8. How much is left? 7. So I'll be marking the 7 by 9 into 18. Okay, this will give me minus 14. And here from 6 I'll get minus 12. Same thing for this also, 6. The second object is excluded. So 6 will give minus 12 here. Then the space left is not enough for accommodating the total 9. So we'll be excluding here. We'll be stopping at this point. This is minus 22. This sum is minus 36. Okay, so we'll be writing here minus 36. After we get the u and c values, we'll be noting down in the note 5. Here we'll get minus 22 and here it is minus 36. Now among these two, which is the least one? Is minus 38 lower than minus 36? Yes. So we'll be killing this node here. We'll be moving on with the fourth node. From here we'll get the sixth node and seventh node. For each we'll be writing u is equal to c is equal to. See here, u as u and c we have written for the node 6, and seventh for the seventh node also u and c we have written. Now we have two options, x3 as 1 or x3 as 0. Okay, if x3 is 1, at that case the if x3 is 1, that means we have to compulsorily include the third object. Okay, so if you include the first, second and third object, I'll get the sum here as 32, and here the weight left is 3, so I'll be including 3 here from the last one, and the profit I get is minus 6. So I'll get the total profit as 38. Okay, so I'll be writing here minus 38. In the second one, the same thing here, but I can't include the third object. Okay, so I'll be leaving the fourth space empty here, so the profit will be minus 32. Okay, that I'll be mentioning here, u as minus 32 and c as minus 38. Now for the seventh one, which is 110, okay, means x3 is 0 here. In this case we are excluding x3. Okay, so I have to go with the fourth object. In this case the first two objects are selected and the third object we are excluding. So instead of the third object, what we are left with is the fourth object, which is 18 into 9, 18 and 9. So here I will be counting the total weight here, 4 plus 2, 6. How much is left? 15 minus 6 is 9. Here I have 9. I can directly include 9 here and the profit is minus 18. Okay. Here also I can do the same thing because there is space for the whole object, which is 9, and the profit is minus 18. So when I calculate the total profit here, it will be minus 38. Okay, minus 38 here and minus 38 here also. Okay, and I'll be including the profits here, minus 38 and minus 38. Now at this point, choose among these two. See here, lower bound is minus 38 here, and here also it is minus 38. So we'll be going for the upper bound. Minus 32 is small or minus 38? This one is small, right? So kill this node. Then we'll be expanding the seventh node here. On seventh node we'll be getting 8th and ninth. This one will be x4 is equal to 1 or x4 is equal to 0. Okay, so we'll be writing here x4. This one is 0, and from x4 means we are excluding the third object here. Okay, means the third object will be excluded here. You only have the option left of the fourth object. Here also we'll get the same answer if we go with the first one, which is including the fourth object. U is equal to c is equal to including the fourth object and excluding the fourth object. If we include the fourth object, here we will get the weight of the object 9 and the profit is minus 18, and here also the same thing, the same answer here we will be writing here. Okay, minus 38 and minus 38. And here excluding the fourth object, that means we cannot include the fourth object, and after the fourth object we don't have any object here, so we have to compulsorily leave the space empty here. Okay, even if we can allocate other objects, we can't, because there are no other objects. Okay, so x3 and x4 are excluded, only 2 and 4 are included. Here the total cost will be minus 20, here also minus 20. Okay, so both u and c are minus 20, so I'll be mentioning here minus 20 and minus 20. At this point select which is the least. Minus 38 is lower or minus 20? Minus 38, right? So tick mark here. So this is the combination which is 1101. We have written here 1101. So this is the answer for the knapsack problem. This is the third type of knapsack problem, which is using FIFO algorithm and branch and bound technique. Okay, so the same question as the previous one. We have 4 items here, and the weights and the profits are given x1, x2, x3, and x4. Okay, so we have to find out the knapsack solution by using FIFO algorithm. So what's the difference is, here we'll be having a global upper bound. Okay, and let's get started and understand how to solve this problem. Okay, so initially we'll be taking the root 1 here, the node as usual 1, and we'll be writing here u is equal to and c is equal to. So we'll be starting from here. 2 will be included here. The first one is included 2 minus 10, then 4 minus 10, then 6 minus 12, and here we'll have 3, so here it will be minus 6. This will give us the minus 38 here. Okay, and here also we'll be doing the same thing. 2, 4, 6, we can't include the 3 here, so the total profit will be minus 10 plus minus 10 plus minus 12, which is minus 32. Here I'll be writing the upper bound and the lower bound, minus 32 and minus 38. Whenever I get a upper bound here, I'll be mentioning that here. Okay, this is minus 32, I'll be writing here minus 32. The next step is, from 1 I can have two paths, x1 is equal to 1 and x1 is equal to 0. Here I'll have the node 2 and node 3, u is equal to and c is equal to. Now for node 2, x1 is equal to 1, so compulsorily we have to include this one. The same thing we'll get here also, so we'll be writing here minus 32 and minus 38. The next one, here we have to exclude the object 1 here, so the total profit will be, when we exclude the object 1, we'll be starting from 4, then 6 minus 12, and here we will have 5 spaces left, so the profit will be minus 10, and here 4 and 6. Okay, so the total profit is minus 12 here, and here I'll get the total profit as minus 32. Okay, so we'll be writing that values here. U is minus 12 and C is minus 32. At this point we have to make a decision. First let's see if the nodes are valid or not. U is minus 32, here also U is minus 32. You have to select the least one. Since both are equal, we will be leaving it as it is. Then C is minus 38. Here U is minus 32. Compare these both. In any case, if C becomes greater, at that time we will kill the node. Is C greater? Is minus 38 greater than minus 32? No. This is smaller. When it's smaller, we'll keep the node. If this becomes greater than the global U value, at that time we'll kill the node. Okay. Since this is smaller here, we'll keep the node. Let's check the next one. Here the U value is minus 22. Here the U value is minus 32. Which is smaller? This one is smaller, we'll keep it as it is. The next one is minus 32. This is also minus 32, so it's a valid node. We'll be expanding both of these now. X1 is x2 is equal to 1 and x2 is equal to 0. Here also the same thing, x2 is equal to 1 and x2 is equal to 0. Here we will get 4 and 5. Here we'll get 6 and 7. U and C. Now see here, x1 is 1 and x2 is 1. So first and second object is compulsorily included here. So when we include the first and the second object here, we'll get the 2 and 4, minus 10 and minus 10, Then we can have 6 here, which is minus 12, and here 3 will get us minus 6, so it will be minus 38. And here the same thing except the last one, so here we'll get till minus 12. The sum is minus 32. We'll be writing here minus 32. So u and c we got, we'll be mentioning here minus 32 and minus 38. Then we'll be checking if it's valid or not. Minus 32 is same as this one, so it's valid, and minus 38 is smaller than minus 32, so it's a valid node here. The next one, x1 is 1, x2 is 0, so second object we have to compulsorily exclude. Okay, so if you exclude the second object, we have to go with the third object, which is 6. Okay, we'll be writing here 6, which is minus 12, 6, 7, 8, 7 is left, so the profit will be minus 14 here, and here it will be 2 and 6, and we can't include the third object, so it will be stopping here. It's minus 22, and here it is minus 36. So it will be noting down these both values here in the fifth node, so it will be minus 22 and minus 36. Now is this node valid or not? U is minus 22, it is minus 32, so the smaller one is minus 32, we'll keep it as it is, and C is minus 36. Minus 36 is smaller than minus 32, so this is also a valid node. The next one, x1 is 0 and x2 is 1, which means we have to exclude the first object and include the second object. So we'll be starting from 4 minus 10, 6 minus 12, 4 plus 6 10. After 10 5 is left, so minus 14, so it will be 14 here, 6 plus 4 10, and 5 is left, 5 means 10 here. Okay, and this one 4 and 6 here, that much only, so 10 and 12. This is minus 22, and this one is minus 32. Okay, so we'll be noting down these values here. U is minus 22 and C is minus 32. So is this valid or not? Minus 22 and minus 32, 32 is smaller, and minus 32 and minus 32, so it's valid node. And the seventh one, excluding both, x1 is 0 and x2 is also 0. When you exclude both x2 and x1, at that time we have to start from the third node, which is 6. We'll be starting from 6 here. When you start from 6, it will be minus 12, and we'll be filling with 9, it's 18. Same thing here also, minus 12 and 18, here it's 9 and here it's 6. Okay, so total profit is minus 30, and here also the total profit is minus 30. So U and C both are minus 30. Okay, we'll be writing here minus 30. When both we get as minus 30, at that time we'll check if this node is valid or not. See here, U is minus 30, here it's minus 32. This is smaller, we'll keep it as it is. C is minus 30 here, and this is minus 32. C is greater, minus 30 is greater than minus 32. So here we will kill this node. Okay, C should not be greater. So we'll kill this node, and we'll move on with the next 3 valid nodes. See here, now we'll be expanding this one. This will be 8th node, and this will be 9th node. Now see here, x2 is over, will be including x3 and excluding x3. x3 is equal to 0. Now when x3 is included from 8, see here, what will be the value of u, what will be the value of c. When 3 are included, we have to include the 3 values here. We'll be including those 3 values, 2, 4 and 6. When we'll include 2, 4 and 6, 2, 4 and 6, then the profits are minus 10, minus 10, minus 12, and here how much is left? 3, so it will be minus 6, so the lower bound will be minus 38, and here 2, 4 and 6, so here the minus 10, minus 10, minus 12, so it will be minus 32. We'll be noting down these both values here. Note down both of these values, minus 32 and minus 38. Now minus 32 and minus 38, let's check if it's a valid node or not. Here it's what U is minus 32, that's the same as this, and C is lesser than this one, so it's a valid node. And here here what will get U and C. If we exclude the third node, that means you have to include the fourth node. Fourth node is 9. Okay, excluding the third node and including the fourth node. If I include 9 here, 4, 5, 6, 6 plus 9, 15, and here the profit is minus 18. Here also the same thing, since it doesn't involve in fraction here, we can take 9 from here. The total profit will be 38. Okay, and here the upper bound also will be minus 38. Okay, so we'll be writing here the upper and the lower bounds minus 38. Now observe one thing carefully. U I got as minus 38, here U is minus 32. Which is smaller? This one is smaller, right? Update this value. When you update this value, this will become minus 38. Okay, and C is minus 38, this is also minus 38, it's same, it's a valid node. Now what we'll be doing is we'll be checking the other nodes if any of these lower bounds is greater than minus 38. Let's start from here. This one is minus 38, this one is also minus 38, it's valid. Then this one, here the lower bound is minus 36 and here it is minus 38. Minus 36 is greater than minus 38, then this node is invalid. Here minus 32, that's also greater than minus 38, this is also invalid. Now we have two valid nodes here which will be expanding. Okay, now observe here one thing carefully. From here, if I'll get two options here, either x4 is equal to 1 or x4 is equal to 0. In case x4 is equal to 1, that means x1, x2, x3 and x4 all are included. If I include all of these at that time, I will not get the proper answer because it will exceed the capacity which is 15 here. Okay, if I include all of this, it will become 21. Okay, so I can't go with this solution. Okay, this is not possible. What about this one? In this one, the node 10, U and C, excluding the last object. If I exclude the last object, what the sum I will get here is, even if I have space, I have to not include the last object. Okay, only 1, 2 and 3. The total profit is minus 32, and here also the total profit will be minus 32. Okay, this one is 6 and here it is minus 12. Okay, I have space still left here because the total sum here is 12 and I have space left here as 3, but I have to not include the last object. Even the fraction of it should not be included. So I'll be keeping this space empty here, and here I'll be getting the answer as minus 32 and minus 32. That I'll be noting down here, minus 32 and minus 32. Let's see if it matches this one. Which is smaller, minus 32 or minus 38? For U it is minus 38, so we'll be keeping it as such. And what about this one, C? Here C is minus 32, which is greater than minus 38. We'll be cutting this node. Coming to 9, we have two options, either going with x4, x4 is equal to 1 or x4 is equal to 0. Okay, 11 and 12. What is the value of U and C in both of these cases? Observe carefully, 1, 1, 0. That means third object is excluded. If third object is excluded, at that time I have to include the fourth object here, which is 9. Okay, so here I'll be getting the answer as 9, which I can include here, minus 18. Here also I can do the same thing since it doesn't involve in fraction, so I'll be getting the sum as minus 38 and here also minus 38. I'll be writing the answer here as minus 38 for both of these. Is this valid? U is minus 38, here also U is minus 38, it's a valid U, and C is minus 38, which is equal to this one, this is also valid. Okay, so this node is valid here. And what about this one? X1, X2 included, X3 and X4 are 0. That means even if I have space, I have to not include X3 and X4. So I have to leave the space empty here. When I leave the space empty, I'll get the sum as minus 10 and minus 10, which is minus 20 in both of these cases. So I'll get here minus 20 and minus 20. Let's note down that value here, minus 20 and minus 20. Comparing minus 20 with the global variable here, minus 38, this smaller, so I'll keep it as such. And what about this one? C is minus 20, which is greater than minus 38. C is minus 20, which is greater than minus 38. So I'll be cutting this node. We are only left with this node if you observe the whole graph here. So this is the correct answer, which is 1, 1, 0, 1. So we'll be mentioning the final answer here, x1, x2, x3 and x4 as 1, 1, 0, 1. Okay.
In this topic, we will be discussing what is P, NP, NP-complete and NP-hard classes. So we'll be breaking down this module into many parts and we'll be discussing each part one by one, okay, by taking many examples. Now see here, the first thing is some algorithms take polynomial time, which is constant power, and some take exponential time, which is variable power. So what is exponential time and what is polynomial time? In polynomial time, we'll have linear, means we have an example of linear search and binary search and insertion sort and so on. So what is the main difference between polynomial and exponential? In polynomial, see here the powers are n power 1 here, and this is log n, and here we have n power 2. Okay, so all these are constant powers, so this will not take much amount of time for large values. Okay, but exponential will take large amount of time. It's 2 raised to n. So suppose that here n power 100 is also under polynomial. I'm just explaining why we differentiate between polynomial and exponential. And 2 power n, for large values of n like 10,000, it will be 10,000 raised to 100. This will be 2 raised to 10,000. If you take a calculator and solve, this will take much larger amount of time. Okay, so after a certain amount of time, after a certain point in the graph, the exponential time will it will increase very rapidly for larger values, whereas polynomial will tend to become stable. Okay, so that's why we have differentiated between exponential and polynomial. Now the main task is to make these time complexities which are in exponential into polynomial so that they will be solved faster. We have to understand two things: non-deterministic algorithm and deterministic algorithm. Suppose that there is a code here a, this calculates the sum of two numbers c is equal to a plus b. Now there is only one line of code here, c is equal to a plus b. I know what does this code do. It will add two numbers which are present in the registers in the memory, and that sum will be stored in c. Okay, when I know what the code does, each line of code what it does, if I know that, it is known as deterministic. Okay, suppose that I don't know what each of the code does. So for example, see here, in this algorithm we are searching a key, means the key we are searching here, and a is the array and n is the number of elements in the array. So there are three line of non-deterministic codes, which are this one, this one, and this one. In these three line of code, I don't know what do these line of code mean choice, success, and failure. I know what it does, but I don't know how it does. Okay, what does choice do? Suppose that there is an array here. At the fourth position, there is an element 9 here. What does choice do? Choice will give me the fourth location. So in J, I'll get 4 here, and key was 9. Okay, so if I pass key here, choice will give me J. J is 4, means at fourth location, key is present. Then we'll be checking if key which is 9 is present at A of J, which is A of 4. Yes, it's present. Then we will write it and we'll call success function. What it does is it will inform the computer that the key has been found. And failure function, if we don't get the key, we'll call the failure function to tell the computer that the key has not been found. Now I don't know how to implement this one. Choice, what does it do? It will just take the key here, which is 9, and it will give me the location. Yet till now we don't know how to implement this one and what lines of code we need to write to get this algorithm done. Okay, so we are just mentioning here as choice, and at which point of time we get to know what does choice do. At that time we'll fill this blank here, this blank space now. Okay, then we will fill the blank space here. Same thing we'll do for success and failure also. And when we are able to do that for the three lines of code, then these three lines of code will be knowing how to implement them. So the whole algorithm will be knowing how to implement it. Then it will become deterministic. Okay, see, initially it was exponential time taking, means it takes a lot of amount of time, but I reduced to polynomial time. This takes polynomial amount of time. Suppose that if I implement this one, I don't know yet how to implement, but there's an idea. If I implement successfully, it will take constant time here, here also constant time, and here also constant time. So overall problem takes constant amount of time, which is polynomial. Okay, so this is just an idea here. If after me someone comes uh, and is able to solve the blank spaces here, then that person will be filling the blank spaces here and writing the and making the non-deterministic into deterministic algorithm. Okay, so to quickly recap, the main difference is the deterministic algorithm, we know each line of code what it does. Okay, we know what it does and how it does, but in non-deterministic we know what it does, but we don't know yet how it does. Okay, so that's the main difference between non-deterministic and deterministic algorithm. The second thing is, what is P? P means deterministic polynomial time-taking algorithm. You can take the example of the algorithm which adds two numbers. Okay, there are many numbers, like take the input of two numbers, add two numbers, and then display the result. In each line of code, we know what it does. It takes the two numbers, it will store in the some registers in the memory, then it will add two numbers and store in the result register, then it will display the result in the screen. Okay, so this is deterministic, and it takes polynomial amount of time. Okay, that means if we calculate the time complexity, it will be in the order of 1, order of n square, or even order of n 100 also, n power 100 also. That's also polynomial only. Okay, don't confuse, it's also polynomial because it's constant power. Okay, so if time complexity is in lying in the polynomial range and it is deterministic, at that time we can call it as deterministic polynomial time taking algorithm. Okay, so the examples are as follows: linear search, binary search, insertion sort, matrix multiplication, merge sort, quick sort, and so on. Because in those lines of code, for each of these, we know what the code is and how it does. And when we calculate the time complexity, it is not coming under exponential. It is in linear amount of time only. Okay. So that is P, which is polynomial and deterministic. The next one is non-deterministic polynomial. See here, initially this algorithm was taking 2 power n amount of time. You can consider another example also. These all algorithms, if you see and calculate the time complexity, it will take 2 power n amount of time. But if we reduce if we reduce that to polynomial amount of time, including some non-deterministic lines of code which we don't know yet, but still there is an idea that it could be reduced in the polynomial amount of time if we successfully implement these three lines of code. Then it is known as non-deterministic polynomial time-taking algorithm. Okay, that is NP. And initially, if we have to write any algorithm, we don't know much about the algorithm. So initially there will be many lines of code which we don't know here. So some only will be deterministic, rest all will be undeterministic. Okay, so in that case, every algorithm when we start it, it is NP only, because it's non-deterministic and polynomial time taking algorithm. And slowly when we get to know about each line of code how to implement, we'll be filling the blank spaces, and then it will become deterministic. Okay, deterministic polynomial time taking algorithm. So therefore we can conclude that these are the set of all the algorithms, and these are the set of algorithms which we have successfully implemented till now. And in future, if we get to know more about the algorithms, different algorithms, we can implement that in polynomial time taking and deterministic, then that will also come under this circle. So the circle of P is constantly expanding whenever we get to know about deterministic and polynomial algorithms. Okay, so remember, NP, and this is the subset of NP, which is P. Okay, the next thing is to approach a polynomial time taking algorithm means, see here, there's a exponential. These are all exponentials. To convert that into polynomial time taking algorithms, there are two guidelines. The first thing is you have to write a non-deterministic algorithm for it. So this is polynomial time taking algorithm, and write an algorithm which takes constant amount of time or polynomial amount of time, but it's okay if you include the ambiguous lines of code, because they could be later fulfilled. Okay, but we'll at least get an idea. Okay, so that's the first step. Form an algorithm which although might be non-deterministic but takes polynomial amount of time. This is more important. Okay, that's the first step. The first step is to write an algorithm which is non-deterministic for having polynomial amount of time. Okay, having polynomial amount of time. That's the first step. The second step to make exponential into polynomial is form a relationship between different algorithms so that if one is solved, rest will also be solved. Okay, so see here, these are all exponential time taking algorithms. So if we solve any, if we form a relationship, means if there are any similarities between any of these, and we note down the similarities in one piece of paper, and then we try to solve the main prototype here, then if this is solved, partially everything will be, every algorithm here will be solved. Okay, because these are all in somehow related to the main one. Okay, so what we are doing is we are picking up each algorithm, forming a relationship with any one algorithm and then trying to solve this algorithm, so that if this is solved partially, each one will be solved. Okay, that's the second step. For this we'll be using a algorithm known as satisfiability algorithm, which is just like a knapsack or traveling salesperson or graph or sum of subset problem, which also takes 2 power n amount of time. Okay, that is known as CNF satisfiability. Okay, in this algorithm we'll be taking this as a base algorithm, and we'll be trying to make a relation with every other algorithm. Okay, so whichever algorithm forms a relation successfully with this one, that will be called as NP hard. Okay, so this is the base algorithm which is chosen officially, and we'll be forming the relationship with other algorithms. Okay, whichever algorithms successfully forms a relation with the main algorithm, it will be called as NP hard. These are all NP anyway, and whichever forms a relation, that is known as NP hard. Okay, and second thing is NP complete. NP complete means whichever algorithm has formed a relation with the satisfiability, means knapsack, traveling salesperson, and sum of subsets and so on. Whichever has formed a relationship with satisfiability algorithm, it's known as NP hard. Okay, NP hard, and whichever algorithm, for whichever algorithm here, we can write a code which is non-deterministic but polynomial time taking. If you can write this line of code here, which is non-deterministic, means some lines of code we don't know yet, but we are able to form an idea of an algorithm which could be solved in the future, and it takes polynomial amount of time. Then this if both the conditions are true, means it's having a relation with the satisfiability also, and the second one is it has an algorithm idea also. Then if both the conditions are true, it is called as NP complete. Okay, so see here, NP means all the exponential time taking algorithms, and P means the algorithms which are successfully implemented in polynomial amount of time, and NP hard means the algorithms which have the relation with the satisfiability algorithm, and NP complete means it has the code also, means the idea, general idea of the algorithm, as well as it has similarity with the satisfiability algorithm. If both the things are true, then it comes under the class NP complete.